Hello, everyone on Zoom, can you hear me?
Ouais, c'est bon. On a du mal à savoir. Je vais chercher l'alternance, mais si je rentre dans le.
Okay, so just for those on Zoom, okay. For those on Zoom, I'm just repeating that I hope you saw the information that I posted on Moodle with the information about the last session, TPTD. So there's one session, there's still another today and another session with me. And then there's one 3-hour session, which is a kind of debrief about the whole course with applied exercises with my colleague Catherine Robert. And then with her again, you will have a practical session on your computers. So just for everybody, make sure you download and install R and Jamodi. Okay, there is the information on Moodle. There's a link. You need to download R and Jamodi, which is, Jamodi is, most of you will know about R, right? Yes? Anyway, R is a statistical software, and then Jamodi is like an added, it's a graphical interface, which makes it much easier to use, and you will be doing a practical session with your own computers in this room, but with data, where you have to analyze data and do various statistical tests. So it's also a good revision for the course. And just to recap that for the exam, you will have a mixture of exercises where you have to do your own calculations, just like we've been seeing as we go. And also, based on the sort of things you will have done in the practical, output of the software, which you have to analyze and decide, which is the right output to look at, find the information, interpret it, etc. Okay, is that clear? And there will be maybe 1 or 2 examples of previous years for you to look at. The other thing is with the questions for the exam will be written in English and in French, and you are free to answer in English or in French. Okay, you can write, if you write it all in French, that's fine. If you write it in English, that's fine. If you use a mixture of both languages, that's fine. And that's all the languages will allow, okay? So you don't need to worry about the language, but yeah. So last time we talked about linear correlation, and I wrote down where we stopped. We just had a couple of slides at the end that we need to look at. So just a rapid recap that we're currently looking at statistical analysis which aim at looking at the relationship between two quantitative variables. Two quantitative variables, and if we're purely looking at association, then with no particular order, then we can look at correlation. but if we are trying to predict one variable as a function of the other, then we need to look at regression. And so far, we just talked about correlation, the different aspects of linear correlation. And so I'm just going to go to where we had arrived, which was testing the significance of the correlation coefficient and the fact that there are conditions to use this, to calculate a linear correlation coefficient and also to use the significance test of the correlation coefficient. In both cases, you need the distribution of the variable to be normal and the constant variance for each value of x, or vice versa. You need a normal distribution, and you need there to be a linear relationship between x and y. If these conditions are not met, you can use the non-parametric equivalence, which is the Spearman correlation coefficient. So what is the Spearman correlation coefficient? So the Spearman correlation coefficient uses ranks instead of the actual values of the data. So the ranks means you classify the variables in the values of the variable in an order from the smallest to the largest, okay? And the rank is first value, second value, third value, okay? That's the rank of the values of the variable. And so what the Spearman correlation coefficient does is, instead of looking at the values, so if I write an example here, you could have two sets of variables. Someone drew the pig again. There was a pig last time. I raised it and someone drew it again. Okay. So if you have two variables, x and y, then if you say the values are okay, then the rank of it, you have to put these values in the right order. So this is rank 1, rank 2, rank 3, rank 4, rank 5, and this is rank 1, 2, 3, 4, 5. Okay? Does everyone understand what the rank is? And so when you calculate the Pearson correlation coefficients, you're going to work with these values, okay? You're going to calculate the R or the rho, and it's going to be with the formula, etc. So this is the formula, and you're working with the values. Whereas when you calculate, so this is for Pearson, when you calculate the Spearman correlation coefficient, you use the ranks and not the values, okay? So when do we use it? We use it in the same to test the association between two variables. When there is, one of the conditions is that there has to be a monotonic relationship between them. So it doesn't have to be linear, which is the case for the Pearson correlation. It doesn't need to be linear, but it does need to be monotonic, which means that you mustn't have a change of direction. When x increases, y must always increase or decrease. You can't have a change of direction. This is not a monotonic relationship, okay? And so how do we calculate this? What's the advantage of the Spearman compared to the Pearson correlation coefficient? There's no normality condition. You can use it in more situations than Pearson correlation coefficient because you do not need the numerical values. So you can see that you can use it for ordinal qualitative variables. So if you were looking at, say, the level of study, you could still rank the values, and so you could calculate the Spearman correlation coefficient. And it can be used to detect some nonlinear association, not all, because you can't use it for this type of situation, but you could, it doesn't need to be linear. So the first thing you do when you want to calculate the Spearman correlation coefficient is to convert the data into ranks. So that's what I did over there. So N equals the number of pairs of data. D is the difference between ranks for two values of a pair of data. And RS is the rank correlation coefficient. So if there are no ties, this is equal. So because, for instance, imagine you could have values, you could have 89 twice, and then you wouldn't know how to rank it. Then you can use that formula. 1 minus 6 times the sum of the differences between the ranks squared over the number of values squared minus 1. This is this formula. And if there are ties, this is equal, then you have to use this formula. But you're always working on the values of the ranks, okay? X and Y are the ranks. So, for instance, and then you can also have a significance test for the Spearman correlation coefficient with the same hypothesis as previously. The null hypothesis is that there is no correlation. The alternative hypothesis is that there is a significant correlation. And depending on the size of the sample, if it's smaller than 10 or greater than 10, you either use the thresholds given in the table to compare your coefficient with the values in the table, or if n is greater than 10, then you calculate the test statistic and compare it to a threshold of a student distribution. And then you conclude concerning the significance. So here we have the weight of 10 newborns. So this is the real weight in grams. And we want to know if there's an association between birth weight and the number of cigarettes smoked during the first 2 months of pregnancy. Okay, so these are two quantitative variables and want to know whether there is a relationship. So first you have to rank the weight. So the weights are already ranked from the smallest to the largest. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then the rank of tobacco consumption. So this is the smallest number of cigarettes smoked. So that's 1, then 3, then 5. So that's the third value, 6, etc. So here are the ranks of the tobacco consumption. Then you calculate the difference between the ranks. So -9, -6, etc. And then you calculate the DI squared. The sum of the DI squared is 276. And so you can calculate the Spearman correlation coefficient as there are no ties using this formula. And this is the Spearman correlation coefficient. So you can interpret it in a similar way to the Pearson correlation coefficient. So what does the fact that what is the range of possible values for a Spearman correlation coefficient? What is the minimum or maximum value it can take?
This one.
That's right, -1 and 1. So it goes from -1 to 1. And what does it mean to have found -0.7? What does that suggest about the relationship between weight and the number of cigarettes? The fact that it's negative. What didn't we not do, which we could have done to start off with? What do I say in stats? It's very important to start by doing what? The hypothesis, but also, so for the moment, we're not doing a test, but before the hypothesis. Yeah, look at the data, right? Yeah. So we don't especially need to look at the distribution, but we can look at the data. If you look at the data, it's harder with numbers, but what do you think the relationship looks like? We have weight, and here we have number of cigarettes smoked. What do you think the relationship looks like? Yeah, thank you. Something like this, right? No? The more, when the one who has, so we're not working on the ranks, but there we have the person who has smoked 1 cigarette is at the weight 2,536.7, and then the one who has the most cigarette consumption, 15. is the weight 1447. So I don't know exactly where the others are, but that's what the negative means, isn't it? Okay? Negative means there's a negative relationship, yeah? It's the same as the normal correlation coefficient. And so we want to know whether this relationship is significant. And so since we're in, there's 10 values, we can look at the table. So the critical value for 10 values for a bilateral test of 5% is 0.648, which means that here we're greater than the critical value, so we can reject the null hypothesis that RS is equal to 0. Therefore, there is a significant negative correlation between birth weight and tobacco consumption in mothers. So the more you smoke, the smaller the birth weight of the baby is if you smoke while you're pregnant, during the first 2 months of pregnancy. So Pearson correlation, Spearman correlation, just those are the formula. Remember that basically you see here that if you look back to the lesson, the formula are similar, but here remember you work with the ranks and here you work with the base values, and the test of the significance for n greater than 10 is the same similar test. For n less than 10, you use this table that I gave here to calculate, to decide whether to reject the null hypothesis or not. Okay, so that was just the end of the lecture on correlation, and now we're going to look at regression. Do you have any questions on correlation? No? Oui.
Ex-aequo sans ex-aequo avec ex-aequo, je peux pas le terme.
So ex-aequo, ça veut dire with ties, means that if you had here, if I had values here, like if I had 89, 89, 76, 31, then when I'm trying to rank them, I have to say this is number 1, this is number 2, and these are both 3, you see? 3, 3. So that's ex-aequo, le rang est ex-aequo, d'accord? And so then what you do, sorry, when you have 2, then the next one is 5, okay? That's what you have to do. And if there are ties, donc des ex-aequo, you have to use the second formula. Do you understand? You can't use the first one. Because the second formula is a kind of special case, but it's the same values that you will, well, you'll get similar values, but oh, I lost my. So we're going to talk about linear regression now. So,
Excusez-moi.
oui.
Moi, j'ai pas compris. Il y a 2 formules pour calculer selon la situation où s'il y a.
Des ex-aequo ou pas.
D'accord.
D'accord? Donc, s'il n'y a pas d'ex-aequo, vous utilisez celle qu'on a utilisée dans l'exercice. S'il y a des ex-aequo, il faut utiliser l'autre formule.
Oui.
Mais attention, les X et les Y, c'est bien les valeurs des rangs. C'est pas les valeurs des en elles-mêmes, quoi. C'est pas les 68, 125, c'est les valeurs des rangs. Right, so this first slide is similar to what we saw earlier. Just to remind you that we talked about correlation, and as I said, correlation is used in cases where we don't know, we give X and Y the same type of role. Il y a encore des questions? Il y a quelque chose que vous n'avez pas compris?
Non, moi, c'est.
Vous voulez? Vous avez eu la réponse, mais vous pouvez me la poser à moi aussi, hein, pas de problème. Ok, so, et vous pouvez poser des questions en français, hein? Vous avez vu, je réponds en anglais ou en français, ou les deux, no problem. We mustn't, the main thing is understanding the stats, okay? The language doesn't matter so much. So, so in the case of correlation, X and Y play symmetrical roles. So we can say the association between birth weight and number of cigarettes, or between number of cigarettes and birth weight. will be the same numbers. Whereas if we're in a situation where we want to use one variable to predict the other, for instance, use waist circumference to predict BMI, or use number of cigarettes smoked to predict the birth weight of a child, then we need to use regression. And you can see that then X and Y are not interchangeable. They play different roles. We're describing how one varies as a function of the other. And so they have different roles and different names. And of course, in theory, you're the one who decides which one you use as an X and which one you use as a Y. But once you've decided, or once I have asked you to look at it in one way, if you did it the other way, it would give you different results, okay? You don't get the same result. So here, Y is called the dependent variable, or the response variable, or the outcome. So that's what we're looking at. And X is the independent variable, the explanatory variable, the predictive variable, the covariable. It's the one that we're using to predict the other. And the reason why it can be called also a covariable is that you can have several X's, because in real life, it's very rare that one variable is totally explained or great, if you explain all the variability of one variable with just one other variable. Usually, in real life, we need several X's to explain sufficiently the variability of the other. But first, we'll start with the easiest case scenario, which is just one variable to explain another. So there's lots of types of regression, and later on we will talk about another type of regression called logistic regression. But linear regression is a case which you understand and which you might well, it's the simplest type of regression. So we'll start with linear regression. So the idea behind linear regression is that the relationship between X and Y can be represented correctly by a straight line. So this means that but the function f of a regression of y on x is describing the variation of the conditional mean of y as a function of x, which means that f of x, the linear regression, f can be written as alpha plus beta x. And this means that y hat, which is the mean value of y for the subpopulation of individuals such that x is equal to x, y hat is equal to this formula. Yeah, because I can hear you very well. I know that when you're sitting in a class, you always think that we can't hear you, but we can. So either you leave the class or speak more quietly. Thank you. So the value of each, you have the y. So here we're looking at BMI, okay, body mass index, and here we're looking at waist circumference. So when you say that there's a linear regression between y and x, and you're supposing that the mean value of y, so for instance, if you look at a waist circumference of 100 centimeters here, you're saying the mean, here are different y's, you see, corresponding to 100. But you're saying that on average, the y should be on this line, alpha plus beta x. And so this means that you're giving for each x, you're giving a mean value of y. But you know that y varies around this value. And so the difference between a particular value of y and y hat, which is the value predicted by this equation, is called an error term or a residual. And it's the difference between the individual value yi and the predicted mean value y hat. Okay? And so what we are going to have to find is what are the values of alpha and beta? How do we get the equation of this regression line when we just have all these red points? We have the x and y values of a certain number of individuals. So we need to find a way of estimating alpha and beta from the data. So we will see how we find alpha and beta. And then what we will want to do is find out whether the slope beta is significantly different from zero, and this will test the existence of a significant linear association between y and x. So why is beta especially important? Because when you write this equation, y hat equals alpha plus beta x, if beta is equal to zero, what happens to y hat? What is y hat equal to? If beta equals zero, it's not a trick question. If beta, it says it there. If beta equals zero, so you cross this out, okay? Y hat is equal to alpha, okay? So this means that y is constant, okay? So it means that whatever the value of x, then y will just be equal to a constant value. So if you wanted to draw it, that would be if we have values y, if we have y and x, if beta is equal to zero, y is just equal to alpha, okay? So if we have that, can you say that there is a linear relationship between y and x? No, because whatever the value of x, y is constant. So there doesn't seem to be a relationship between y and x, okay? That's why beta is particularly important, but we will also you can also test whether alpha is equal to zero. So now the question was, how do we estimate alpha and beta based on just a whole load of points? How do we find the value of alpha and beta, okay? We've got a whole load of points. How do we find the best line? Is it here? Is it here? Is it here? How do we find it? So what you have to do, there are different methods that you can use, but the one we're going to see today is the least squares method. So the idea is to minimize the distance between the observations, x, y, and the regression line. So we want to minimize, we write all the distances here between the points and the line. So represented, I drew a few in yellow. And we want to find the line, the blue line, which minimizes all the distances. So you have to imagine all the yellow lines, so parallel to the y-axis. And we want to find the blue line, which minimizes the residuals. So to calculate that, we will calculate the sum of the squares of the differences between each point and the line, so-called sum of squares of differences. And then we will say that, so this is what it is equal to, y minus y hat, and y hat is alpha plus beta xi, and we're trying to find, these are the unknowns, alpha and beta. So you do this using partial differential equations, not partial differential equations, sorry, partial derivatives, that's what I meant. And so you can find A and B. You can demonstrate it mathematically. We're just looking at the formula. You can demonstrate that A and B are estimations of alpha and beta that minimize the sum of the squares differences. So you get B estimates beta and is the slope, and A is equal to the mean of y minus B times the mean of x. So you have to start by calculating B and then you find A. But if we have, imagine you have 50 people and you measure their body mass index and their waist circumference, then you'd get a whole series of red dots. If you measured waist circumference and body mass index on another group of people, would you get the same red dots? Would you get the same points? No. And then would you get the same line? No. So this means that, the same as always, depending on your sample, you will get different values for alpha, for the estimations of alpha and beta, different A's and B's, which means you'll get a slightly different line, okay? So that's a bit of a problem because you don't know if the sample you have is a good representation of the population. So you can give the variance and standard deviation and or the standard area of B to describe the variability, and you can even calculate a confidence interval for the line, and so for the slope, and the alpha, and the A. So we said earlier that the most important parameter in this formula, in the regression line, is the slope. So you can test the significance of the slope and the A, the alpha, by using this test. Beta equals 0 means there's no linear association between X and Y. That's the null hypothesis. And beta different from 0, there is a significant linear association. You use that test statistic. It follows a student distribution. And the same as before, you have to check the assumptions that Y has a normal distribution and it has a constant variance for each value of X. And check that there is indeed a linear association between X and Y and not something with a strange U shape or upside down shape. So for that, what you need to check is equality of variances, linear association, observations independent and identically distributed, and normal distribution. And the assumptions here, you can check by looking at the conditions on the residuals, and this translates to these conditions on the residuals. Which is that the residuals would be independent, have a normal distribution, and have equal variance for all values of X. So the way it looks, if you're trying to check, so remember that the residuals are the distance between the Y and the line. And so these residuals, which we call epsilon, are supposed to be normally distributed around 0, because they're supposed to be centered on the line, with a variance of sigma squared. And so to check that the variance of the etas is constant, graphically, you can look to see that the distribution of the point around the regression line is similar, whatever the values of X, okay? So if that's the case, if the size of the variability is similar, that means we have a constant variance, and we can say that we have homoelasticity. If, on the other hand, you can see that the distance around the line is increasing or decreasing, it changes with the values of X, then the variance isn't constant, and so we'll say we have heteroelasticity. And so what you can do to check that the residuals are right, you can trace residuals versus the predicted values. So when you do the practical, you'll be able to see a few examples of that. So another way to check homoelasticity, you can either look at the basic graph, or you can plot the residuals against the predicted values. And what you want is for there to be no visible tendency, a decrease or an increase with predicted values, but just a random distribution around the line. To check for independence, it's the same. You don't want to see any kind of pattern above and below the 0 line. You want to make sure that the residuals are randomly distributed around the line. And you also need to check whether the distribution of the residuals is normal. So you can do this with various graphs, or with the normality test, one of the normality tests that we saw before, so such as this one. So if you have, remind me, what is the null hypothesis of all the normality tests? The null hypothesis for a normality test is always, it says it there, Bishop-Horowitz is the name of the test, that the hypothesis is always that whatever you're looking at follows a normal distribution. Okay, so that's the null hypothesis. And the alternative hypothesis is that they do not follow normal distribution. So if you find a p-value for a normality test that is 0.97, would you conclude, do you reject or do you accept the null hypothesis? And do you conclude that that the residuals follow a normal distribution or not?
Yes.
Yes, what? They follow a normal distribution because we do not reject the null hypothesis, and the null hypothesis is that they follow a normal distribution, okay? So that was just to recap. So in the example that I've been looking at from the beginning, BMI and waist circumference, okay? So we're trying to see, can you predict BMI based on waist circumference? You can see here that this is the type of output, so it won't always look the same, but this is the type of output that you will see from software. So this is one sort of output, and then when you look at Jamovi, you will see another type of output. But what you will always have, so I asked for a regression of BMI on waist. So which one is Y and which one is X? You can't tell by looking at that, but from what I said earlier, which one is BMI, Y and which one is X? Y is BMI and waist is X, okay? So you can get a clue from what I wrote here. So here, BMI does not have a coefficient because that's what we're looking for, but waist has a coefficient. So this is what? What did I call it in all the lesson? What do you think this represents? Coef in front of waist. What did we call it in the rest of the lecture? Yeah, but what is it? What did I call it? Is it alpha or beta? Beta. I called it beta, okay? It's the slope. And this const as in constant is the value of alpha, okay? So if you have to write it as an equation, so instead of writing y equals alpha plus beta x, we can write BMI equals minus 551 plus 0.37 times waist. Here is the standard error. Here is the test statistic and the p-value associated with the test. What is the null hypothesis of the test for the beta, which we saw just a little bit earlier? What are we testing here? If you test the coefficient, this is the estimation of beta. What is the null hypothesis? Do you remember? I said here, when we do a test here, the null hypothesis is beta equals 0, okay? And the alternative hypothesis is beta different from 0. And the same for the alpha. So here, if the null hypothesis is beta equals 0, and underneath the null hypothesis is alpha equals 0. So what do you conclude? If these are the p-values, what do you conclude about alpha and beta? N'est pas égal à 0. We reject the null hypothesis, which means that they are significant. So our equation is valid, okay? There is a linear relationship between BMI and waist. Here you have the confidence intervals for the coefficients, and the same. You can see that this confidence interval does not contain 0, okay? So if it does not contain 0, that's another way of saying that it's significantly different from 0. It's another way of looking at that. In the same, this confidence interval does not contain 0. And the interpretation is that an increase of 1, if we have measured waist circumference in centimeters, then this means that an increase of 1 centimeter of waist circumference leads to a mean increase of 0.37 kilograms per meter squared in BMI in women. I said in women because I didn't tell you, but the study was in women. So that's the interpretation. What would be the interpretation of alpha here? So I said this is what beta means. What does alpha mean? How would you, in words, how would you say it compared to waist and BMI? Minus 551, what does that mean? So it looks a bit strange. What would it mean? It means if the waist circumference is equal to 0, which is not possible, but okay. If the waist circumference is equal to 0, the BMI is equal to minus 551. So in this case, it's a bit strange because it's not possible to have that type of Okay, but so if we go, so what do I write here? BMI or weight? BMI.
Mhm.
Here I write weight, okay? And here it says that, okay, it's something like this. Okay, except that, is it possible, oh, sorry, not weight, sorry, waist. Waist. So is it possible to have a waist circumference of 0? No, okay, so I'm assuming that this study must have been done probably, say, on a certain, so I don't know, say that here, the points we had would have been here, okay? And so actually, we will see later that you are not allowed to look at the relationship outside the region where your data was, okay? You can only use your formula for in the interval in which your data was. So if you only had women with waist circumferences between, I don't know, 40 and 120, then your formula that you found, BMI equals, the formula BMI equals minus 551 plus 0.37 waist, can only be used for women between 40 centimeters and 120 centimeters waist circumference, okay? That's where your formula is valid, because maybe for babies or for smaller children, it goes like this, or it goes like this. You don't know what it looks like. It's just the interpretation. If you write 1 here, then you can see that if you increase from, say, 31 to 32, then BMI is going to increase by 0.37 times the difference. Do you see what I mean? Okay. So it's just that you could say an increase of 10 centimeters will lead to an increase of 0.37 times 10. It's just the way of interpreting. Yes.
Vous avez commencé à expliquer le waist. Le P c'est 0,0 et j'ai rien compris après. Et vous pouvez le dire en français si c'est.
Oui. Donc, ce qu'on doit savoir interpréter de ce tableau, c'est que ici, on a, ici, c'est la valeur de l'estimation du coefficient. Donc, on l'appelle B, c'est l'estimation de bêta.
Oui.
Donc là, je l'ai arrondi, j'ai fait 0,37. Ici, c'est l'estimation de la valeur de alpha qui est l'ordonnée à l'origine, la constante, et je l'ai appelée, j'ai arrondi à moins 5,51. Ici, on a en fait l'erreur standard du coefficient. Ici, c'est la valeur de la statistique de test, du test qui est ici, là.
Oui.
C'est ça c'est le
Oui.
T0,
Oui.
d'accord? Et ensuite, on a la p-value de ce test. D'accord.
Ça veut dire quoi?
Donc la p-value, c'est comme d'habitude, on a ici l'hypothèse nulle, enfin ça correspond au test où l'hypothèse nulle de bêta égale 0, que ça est égal à 0. Donc si j'ai un petit p qui est inférieur à 0,05,
oui.
Si je suis à un risque d'erreur de 5%, ça veut dire que je rejette l'hypothèse nulle.
Oui.
Donc bêta est significativement différent de 0. Donc je peux bien utiliser ce coefficient parce qu'en fait, en fonction des échelles et tout ça,
oui.
Des fois, vous allez avoir un bêta très petit, mais il est significatif, ou au contraire, vous allez avoir un bêta qui vaut 12 000, mais il n'est pas significatif parce que vous êtes sur des échelles très, très importantes. Donc, ça vous dit la significativité du coefficient. Et j'ai dit, on peut aussi regarder l'intervalle de confiance ici. L'intervalle de confiance du bêta, il est entre 0,2 et 0,42. Ça veut dire que le vrai bêta, c'est toujours pareil, hein, comme en stade depuis le début, Le vrai bêta, on ne sait pas où il est. On a une estimation de 0,37 où on sait qu'il est avec une probabilité de 95% entre 0,32 et 0,42. Cet intervalle ne contient pas 0 et donc je suis significativement différent de 0. Et le fait que je sois significativement différent de 0, ça veut dire que je peux écrire cette équation et dire qu'il y a bien une vraie relation entre la taille, le tour de taille et le BMI. Et je peux m'en servir pour faire des prédictions. Et pareil pour le alpha est significatif, sauf que le alpha, c'est moins grave, parce que si ici le alpha, il valait 0, mais que le bêta est quand même significativement différent de 0, vous pouvez avoir une relation entre quoi et, enfin, entre le x et le y, d'accord?
Oui.
C'est bon?
Oui, je pense.
Donc ensuite, so we can also, so as you've noticed, correlation and regression are both used in similar situations with X and Y quantitative, but with a slightly different question. But there is a relationship between the correlation coefficient, the Pearson correlation coefficient, and the slope of a regression line. And this relationship is given by R equals B times, so that's the slope, standard deviation of X over standard deviation of Y. And you can write it, of course, the other way round, which is B equals R times standard deviation of Y over standard deviation of X. And if the standard deviations are equal, then the correlation coefficient, the Pearson correlation coefficient, will be equal to the slope. Now, this is something which we will talk about again also maybe next time. I'll just give a quick explanation here because it's about the relationship between linear regression and analysis of variance, which we will look at either today, but more likely next week. And it's a way of just a way of looking at the data. So when we are looking at Y and X, okay, we're looking at trying to explain why does Y vary, okay? How can we explain that all the values of Y are not the same? So there's a difference between each of these Ys, the observed values, and the mean value of Y, okay? So that is the total variability of Y, can be represented with these yellow, orange bars, yeah? When we do a regression line, we say actually there is part of the variability of Y which can be explained by what happens with X, okay? So for instance, if you look at this bar, you will say, okay, Y is this much different to the average of Y. But if we have X, then we can say this line explains that much of the variability of Y. And there's still a little bit of the variability which is unexplained, and that we call the residual variability. So it's a way of decomposing total variability into variability explained by X, which is what you get from the regression line, and residual variability, which is we're still not quite on the observed value, okay? And we'll talk about that more later when we look at analysis of variance. Another thing which is very important to know about is the square of the correlation coefficient, which we call the coefficient of determination R squared. R squared is the percentage of variance explained by the regression. This is how you can calculate it. So it's either the square of the correlation coefficient R, or you can also calculate it by looking at the explained variance over the total variance. So I use the colors yellow and orange because you're basically looking at the ratio between this variance, this explained variability over the total variability. But also what it's showing you is that, and you can see it graphically, can you understand that the closer the closer the points are to the line, the more it means that the line explains the variability of Y. And the further away we are from the Y, from the line here, then there's less variability explained by X. So here we have weeks of gestation, so how many weeks a baby spends in the mother's tummy, okay, for a human. And this is the birth weight in kilos, okay, so between 1.75 and 4 kilos. So the longer the baby stays in the tummy, the bigger the birth weight, yeah? You get that? So if we had points which were perfectly aligned on the line, that would mean that when we know the gestational age, so how many weeks they spent in the, if all the blue points were on the line, then you can say that if you have a baby that was born at 38 weeks, its weight will be 3.2. If the baby's born at 36 weeks, its weight is 2.7. You could have a perfect coefficient of variation of determination would be r squared equals 100%, okay? And the more the points are dispersed around this line, so for instance, here, we can see that even with knowing the weeks of gestation, 38, we still have some babies who weigh less than 3 kilos and some babies who weigh 3.5 kilos. So what does that mean? That means that, okay, gestational age is important to explain birth weight, but there are other factors, maybe genetics, maybe what the mother ate, etc. And so here, the greater the r squared, the more variability is explained by x. If the r squared is low, it means that there are many other factors which we haven't accounted for, which explain birth weight. Do you understand that? Yeah? So this is important in statistics because obviously it's very rare to have one variable which completely explains the variability in another. And the closer the points are to the line, the greater the r squared, the further away and the more variability is explained. So here we're saying, for instance, that 75% of the variability of birth weight is explained by gestational age, so that would be very big. But in reality, usually we're much lower. It means that, say, 43% of birth weight is explained by gestational age. That means there's lots of other factors which we still need to take into account to explain birth weight. Est-ce que ça va? Je le redis en français. Vous voulez que je crie plus fort? Ça va? Oui? Voilà. So, important comments. So this is a star slide. You can put a star on it. It's an important, you need to remember those 3 things are important. So you mustn't use a regression equation to make predictions if there is no significant linear association. So if you find that the test does not reject the null hypothesis, okay, so if you do not reject the null hypothesis that beta equals 0, then even though you have a value of beta, you must not use the equation, okay? Because it's not significantly different from 0. So you're not allowed to use this equation to make predictions. Do you understand? That's the first point. The second point is the use of the regression line to make predictions imposes that you stay within the limits of the available data. You cannot extrapolate. So that's what I was saying over there, okay? If you constructed your regression line using data for women with a waist size between 40 and 120, you can't use it to predict the BMI of a child with a waist circumference of 25, okay? Because your equation was constructed on a certain population, okay? And this one is similar, but this is about the values of your data. And this one is about not making predictions concerning a different population to the one which the studied sample was drawn. So if you did your study only on, say, African women, okay, between these 2 weights, you can't use this equation for European women, okay, because there might be other characteristics. You have to use it in the population that you used, or for instance, you mustn't use it in men if you've done it on women, okay? So these are important points concerning regression. So this is not really a take-home message, but the different formula that you need to know about, and mostly all the different comments. Also, these comments are important. So do you have any questions on linear regression at this stage? No, you understand? Right. Any questions on Zoom, if I haven't lost them? On which date it will be? What are we talking about? You're talking about the exam. We don't know, I don't know the exact date. We just said that it was in what week did we say? 20 to 29th of May, right? Yeah, that's the week. Okay, so the next part is about multiple linear regression. So I said several times that in real life, we don't usually just have one single explanatory variable, which is what we've seen so far, simple linear regression. In real life, we usually have several explanatory variables, x1, x2, x3, so several independent variables, and we call that multiple or multivariable linear regression. For instance, to predict BMI, we don't just consider waist circumference, but also the length of the leg, the length of the arm, the head circumference, what else? Now you have to be careful because the linearity in this equation concerns the beta coefficient. So it's the fact, this model, for instance, is also what we call a linear model. It's the linearity between y and beta. So we've mostly just seen very simple models and called them linear regression, but you can have much more complex models. So what is the interpretation of the coefficients beta 1, beta 2, beta 3? So beta 0 is what we call the intercept, or I called it alpha previously, but sometimes we call it beta 0. It's the one that is not associated with the variable. So it's the value of y when all the explanatory variables are equal to 0. When x1, x2, and x3 is equal to 0, then y is equal to beta. And then there's a residual when you're not looking, when you're looking at exact values. But the expected value of y is equal to beta 0. And beta j is the variation in y for an increase of 1 unit of the variable xi if all other explanatory variables remain constant. And epsilon, we've seen it before, we called it the error term or the residual, is the random part of the model. And we assume that residuals are independent and normally distributed with a mean of 0 and constant variance for all the values of the vector x. So what can be the type of the explanatory variables xi? These variables can be quantitative or qualitative with 2 categories, binary, or even qualitative with more than 2 categories. So this is, be careful because this is an extension of what I said before, where I said y and x have to be quantitative. That's the simplest way of doing it. But you can also have x as a qualitative variable, either with 2 categories, in which case you introduce the variable in the model as an indicator variable with x equals 1 for the category of interest and x equals 0 for the other. And if you have more than 2 categories, you can replace this variable with n classes with n-1 variables with 2 classes. So we'll start by looking at an example of an association. And I will explain this in a minute, so don't worry if you didn't get that. I'm going to explain it, give an example. So here is a similar output of what we saw earlier. It's the we're looking at the regression or the association between glucose level in women and practicing a physical activity at least 3 times a week. Okay, so here, if you had to write the equation, you can see here I did the association. I want to explain glucose level based on physical activity, so I called it exercise. So if you look at this and this, what do you think the Y variable is? Which one is the Y variable? Is it glucose or exercise? You're trying to explain the glucose levels as a function of physical activity, of exercise. So which one is the Y and which one is the X? Good. Glucose is the Y and exercise is the X, okay? So here, if you had to write the equation like we did before, it's a simple linear equation. What would you write using the coefficients in the output? So you said glucose is Y, so glucose equals, yeah, 97 plus,
Minus 169 physical activity.
times physical activity or times exercise. Yeah, that's right. So 97 minus 1.7 times exercise. And so is this, is beta significantly different from 0 in this example? Yes, why?
Because P is less than.
Yeah, very good. The P is lower than 0.05, or the confidence interval does not contain 0, right? It goes from minus 2.6 to minus 0.8. So there's a significant difference. And so we can see that glucose level is 1.7 times lower on average in women who practice a physical activity at least 3 times a week. So that's because we just made it into a binary variable, okay? So this is the first variable. You need the light on, or can you see well enough? I write on the board. Okay. So here, we're writing glucose equals 97.4 minus 1.7 times exercise. And exercise at the moment is equal to 1, they do 3 times a week or a week, greater than 3 times a week, and 0 less than 3 times a week. Well, I don't know whether you call it complete. I think 3 times a week is already quite a lot. So that's the first example. So that's the same as what we were doing before. Now, if you wanted to have physical activity coded in 5 levels, so instead of having exercise like this, you have a variable called physical activity, and it goes from 0 to 5. 0 to 4. 1 to 5. I don't know why I like 0 to 4. 1 to 5. Sorry. 1, 2, 3, 4, 5. So the more 1 is the least activity. How much more active are you compared to other women your age? So 1 is much less active, and then etc. And this is much more active. Okay. So this is, what type of variable is this? What type of variable is it? Quantitative, qualitative, ordinal?
Ordinary.
Qualitative, ordinal variable, yeah? Because we can, it's not quantitative, this is just, I could write 0, 1, 2, 3, 4, or 1, 4, 6, 8, 10. It's just a code. So the question is, how do we put, if we want to put this variable into our model, how can we do it? Can we put it in? So what we're going to do is we're going to see that this is one variable with five levels, okay? We're going to transform it into a variable, into 4 binary variables. So binary means with 2 levels. So is that possible? What we're going to do is we're going to create one variable which is called x2, which is equal to 1 when phys is equal to 2 and 0 otherwise, okay? And then x3 is equal to 1 for phys equals 3, 0 otherwise. And then x4, 1, 0, and x5, 1, 0. Now, do you think that these 4 variables is equivalent to this variable? Can we get all those combinations? Does that enable me to get these ones? So let's see. So here, this is x2, this is x3, this is x4, and this is x5. So when phys is equal to 1, what is x2 equal to? Vous avez compris ou pas?
Non.
Ok, c'est bien. Je fais mon petit tir au tableau, comme ça comprend. So, we have one variable which has 5 levels, 1, 2, 3, 4, 5, okay? And we're going to replace one variable with 5 levels by 4 variables with 2 levels. So I said x2 is a new variable, which is equal to 1 when phys is equal to 2, and it's equal to 0 in all the other cases. So when phys equals 1 or 3 or 4 or 5, it's equal to 0, okay? And here, x3 is equal to 1 when phys equals 3, and 0 otherwise, okay? So if we try and see, does that cover everything? So when phys equals 1, what is x2 equal to? 0, what is x3 equal to? 0 is 0. When phys equals 2, what is x2 equal to? 1. x3 is 0, 0, 0. x3, 0, 1, 0, 0. 0, 0, 1, 0. Okay? Do you understand or not? Yes, me.
Vous avez écrit dans entre parenthèses plus grand que 3x
A week, par semaine.
Ah.
Donc plus
Ça
de
veut
3
dire
fois
quoi?
par semaine. Parce que la variable à la base, ça veut dire l'activité. Dans la variable suivante, ici c'était. Là, c'était juste une variable binaire qui était soit elles font du sport plus de 3 fois, au moins 3 fois par semaine, ou elles font du sport moins que 3 fois par semaine. Il y avait une variable binaire au début, juste une variable binaire. C'est bon, c'était une variable qu'on a définie qui s'appelait exercise. C'était une variable oui-non, binaire. Donc on la mettait dans le modèle, on a discuté, on a trouvé ça. Ensuite, on est en train de dire, si on voulait une variable un peu plus précise que 3 fois par semaine, parce que moi, je ne fais pas beaucoup de sport et je trouve que déjà, quand je fais du sport 1 fois par semaine, c'est bien, je suis fière de moi, ok? Donc peut-être on a besoin de savoir un peu plus que juste 3 fois par semaine ou rien, ou tout le reste.
Ok.
Donc on crée une variable qui, elle, est codée en 5 catégories et qui donne des niveaux d'activité. Alors en fait, on aurait peut-être pu écrire beaucoup moins active que les femmes de votre âge, c'est de faire rien du tout par sport par semaine. Le deuxième, somewhat less active, c'est faire du sport 1 fois par mois. L'autre, c'est à peu près pareil, c'est 1 fois par semaine. Vous voyez, et on fait des catégories. Et on est en train de se dire comment est-ce qu'on met une variable avec 5 catégories dans un modèle de régression linéaire. Je suis en train de vous expliquer ça. Et comment on fait? On est obligé de transformer une variable qualitative avec 5 catégories. On est obligé de la transformer en 4 variables binaires. C'est comme ça. Et donc là, je vous explique, parce qu'au début, on se dit, mais on ne peut pas faire, c'est pas pareil. Une variable avec 5 catégories et 4 variables binaires, est-ce que ça couvre bien tous les cas de figure? Et là, c'est ce qu'on a vu là-bas dans le tableau. Que si on donne aux 4 variables binaires, on dit qu'elles prennent la valeur 1 ou 0 pour chacune pour un niveau, le dernier niveau ici, il est couvert par le cas où toutes ces 4 variables, elles valent 0. Donc là, on regarde si une variable a 5 niveaux, ça peut se décrire par 4 variables binaires à 2 niveaux. Est-ce que ça couvre toutes les possibilités? Et la réponse est oui. Et après, pourquoi est-ce qu'on fait ça? Parce qu'ensuite, vous allez voir, on peut rentrer du coup ces 4 variables dans le modèle de régression linéaire. Alors que c'est plus compliqué. Bon, c'est toujours pareil, vous êtes à un niveau où je peux vous dire, en gros, c'est plutôt ça qu'il faut faire que de rentrer, je dirais, directement cette valeur-là, parce que qu'est-ce qui va se passer? Si on rentre ça dans le modèle de régression linéaire, lui, il va prendre le 5 pour un 5 et le 3 pour un 3, comme si c'était une variable quantitative. Et c'est pas ça qu'on veut, en fait. D'accord? Donc, c'est pour ça on le considère bien comme une variable qualitative, mais il faut quand même le transformer en 4 variables qualitatives binaires. Donc là, c'est juste un petit trick statistique pour dire comment je fais pour transformer une variable à 5 niveaux ordinal en 4 variables à 2 niveaux. Je fais comme ça.
Mais ça sert à quoi alors de mettre 1, 2, 3, 4? C'est pour mettre l'ordre ou
C'est qu'au départ, le gars ou la femme qui a fait l'étude,
oui,
elle l'a codé comme ça. Mais après, le statisticien, il nous dit, ben, il faut mettre cette variable-là dans un modèle de régression linéaire. Il faut faire autrement. D'accord?
donc ces valeurs-là,
on va pas s'en servir.
Voilà, donc je voulais savoir.
Et c'est pour ça que tout à l'heure, je dis, on aurait pu les appeler 0, 1, 2, 3, 4, ou 1, 4, 6, 8, 10,
Oui.
d'accord?
Si.
Alors, so these are called dummy variables. They're called dummy or indicator variables because they don't correspond to anything. They are just an indicator. Okay? So, voila. So then we will be able to put these variables, so we call them the binary variables, you see, physac 2, physac 3, physac 4 et physac 5 is what I call x2, x3, x4, x5, okay? So we can put them in the model like this, okay? And so then we have y égale alpha ou bêta 0, l'ordonnée à l'origine, the intercept, plus bêta 2 physac 2, plus bêta 3 physac 3, plus bêta 4 physac 4, bêta 5 physac 5. And then this is just to show that this is equivalent. So that's the same as that. And then the interpretation of the coefficients will be the value. So this is important. You can write it because I didn't put it on the slide. So how we interpret the model. So we write the new model like this. Glucose equals, so beta 0, this is the same as the alpha before, okay? Plus beta 2, I'm going to call it just x2 because it's quicker. Beta 3, x3, beta 4, x4, beta 5, x5. And then if we find a value of beta 2, which is, for instance, 1.3, okay? 1.3, for instance, and then beta 3 equals 1.6. Beta 4 égale 3.2, comme ça. 4.5. This means that the level of glucose for someone who does sport, who is at this level, is 1.3 times, so it should probably be actually the other way around. It should probably be minuses. Voilà. Okay, I'm not sure. So the level of glucose for someone who does sport a little bit less than normal would be lower by minus 1.3 compared to those who are much less. See? Parce que en fait, je crois que le glucose, il diminue plus on a de l'activité physique.
Oui.
Voilà.
Ah, ok.
Donc je me suis dit en l'écrivant, il faut que je mette des signes négatifs, sinon ça ne marche pas. Vous voyez? Mais bon, ça, moi je suis prof de stats, hein, faut pas qu'on m'en demander. Ok, mais voyez le principe. Donc ensuite, c'est juste que du coup, vous allez avoir à chaque fois, ça va comparer le bêta 2, ça compare à un niveau de 0 en fait. Et on va voir des interprétations tout à l'heure, donc bon, voilà, on va continuer. So this is just how you introduce this variable in the model. Donc ensuite, this is when you have one variable which is qualitative, and you want to break it up into several variables. Now, if we go back to the principle here, which is the fact that often we want several explanatory variables to explain glucose, to explain the why. So here, the glucose level is associated maybe with physical activity, but also with other variables such as drinking alcohol, age, etc. So the idea is to adjust the association between glucose level and physical activity on other variables, okay? So if your aim as a scientist, so this is important if you go on to do research or whatever, okay? If your aim as a scientist is to know whether there's an association between glucose and physical activity, it's just as we said earlier, there might be an influence of physical activity on glucose, but there's a lot of other things that influence glucose. So you need to make sure you also take these into account to see what is the real independent influence of that physical activity on glucose. Because if all the women who do more sport are also younger, eat more healthy food, drink more or less alcohol, I don't know, maybe more. But anyway, then it will impact your glucose, okay, levels. So this is why we do multivariable models. And so if you compare what we found here, when we had just exercise in the model, the influence of exercise on glucose was minus 1.7. If you look here, when you take into account age and drinking habits and BMI, there is still an influence of exercise on glucose, but it is not as strong. You see, it's minus 0.95. And it's still significant. There's a significant relationship. The p-value is still less than 0.05. And which variables here are not significantly associated with the glucose level? If you look at this here, which one is not significantly associated with glucose level? Si BMI is less, le petit p il est moins que 0,05. Donc ici, on rejette l'hypothèse nulle où ce bêta est égal à 0. Par contre, là, drink any, this one is greater than 0.5. So this means that this variable is not significantly associated with glucose. Okay? C'est bon? Oui.
Est-ce que vous pourriez expliquer l'histoire avec le P supérieur à T quand c'est supérieur, c'est chapiroïque?
Non. Ça, c'est la p-value. Tout oui, ça, c'est la p-value du test statistique. En fait, ici, c'est le test statistique, c'est les bêta. Donc, je mets I parce que ça peut être le 2, le 3, le 4, le 5 égale 0. Et on calcule une statistique de test pour chaque bêta qui est B sur S carré B, enfin, il y a la formule dans le test. Ça, c'est la statistique de test. Pour utiliser ça, il faudrait avoir la valeur seuil de la loi de Student et aller regarder dans la table. En fait, dans les logiciels, ils vous donnent toujours la statistique de test, mais vous pouvez pas vous pouvez vous en servir, soit aller regarder dans une table, et ils vous donnent la p-value. Donc, c'est pas le test de Shapiro-Wilk, c'est le test de la significativité du coefficient. Et c'est la p-value, donc après, c'est je regarde par rapport au risque d'erreur, qui est souvent 5%, et je rejette ou pas l'hypothèse nulle de la significativité, en gros, du coefficient. Vous avez compris?
Voilà.
Yes.
Drink and ça veut dire.
Ouais, ça veut dire la consommation d'alcool.
Donc, la consommation d'alcool a un effet sur la variation du glucose, c'est ça?
Non, parce que c'est pas significatif. Le bêta, ici, vous voyez ici le petit p, il est supérieur à 0,05. Donc, on ne rejette pas l'hypothèse nulle que bêta est égal à 0. Donc, en tout cas, dans cette manière de mesurer, dans cette étude, le fait de consommer de l'alcool, alors on ne sait pas comment c'était mesuré.
Oui.
Voilà, peut-être c'est juste quelqu'un qui consomme, d'accord, évidemment, si vous consommez des litres et des litres d'alcool, ça va forcément avoir une consommation. Bon, voilà, ici, dans cette étude-là, ça n'impactait pas. Donc ici, l'interprétation, the interpretation is that for a constant, when you have several variables here, it means for constant age, alcohol consumption, and BMI, the level of glucose is on average 1 milligram, donc en arrondissant de 0,95, 1 milligram per deciliter lower in women who practice a physical activity at least 3 times a week compared to those with less physical activity. So each coefficient gives the increase or the decrease, if it's positive or negative, in glucose level for an increase of 1 unit of the corresponding, there's a P missing, variable, all other variables being kept constant. Donc là, c'est très important, c'est on montre qu'il y a un effet de l'activité physique sur le glucose à âge égal, consommation de boisson égale et poids égal. Donc on montre que il y a bien une influence indépendante de cette variable sur le glucose. Here's another example with in the regression of systolic blood pressure as a function of gender, age, gender times age, height and weight, tobacco and alcohol, okay? So the PAS, pression artérielle systolique, j'ai mis quoi? Systolic blood pressure, oui, c'est ça. Is it a function of le sexe, l'âge, etc. So here, if you look at the p-values corresponding to the coefficients, tell me which variables are not significantly associated with systolic blood pressure. Age and tobacco consumption. OK? Vous avez compris? Oui. Non. Oui, je sais même plus quelle langue je dis. Donc, ici, on regarde la régression de la pression artérielle, parce que j'avais l'impression de l'avoir dit en français, donc je me dis, on regarde quelle est la relation entre le sexe, l'âge, la consommation de tabac, alcool, taille, poids sur la pression artérielle systolique. Et ici, je demande quelles sont les variables qui ne sont pas significativement associées à la pression artérielle systolique. À 0,05.
À 5%, pardon.
Oui. Parce que comme dans toujours, le test statistique, mais là, si c'est supérieur à 0,05, ça veut dire qu'on ne rejette pas l'hypothèse nulle. L'hypothèse nulle, c'est que ce coefficient est égal à, enfin, n'est pas significativement différent de 0. Donc ça veut dire qu'ici, et voyez, regarde, l'intervalle de confiance de ce coefficient, il comprend 0. C'est-à-dire que la vraie valeur du coefficient, elle n'est pas significativement différente de 0. Ça veut dire que c'est dans votre équation, qui est comme celle-là, au lieu de glucose, il y a marqué pression artérielle. Mais ici, le bêta qui correspond à âge, il est égal à 0. Donc s'il est égal à 0, c'est-à-dire qu'il n'y a pas de relation entre l'âge et la pression artérielle systolique. Vous voyez ce que je veux dire?
Ok.
Vous avez compris? Oui. Est-ce que tout le monde a bien compris ça? Vous voulez que je le dise en allemand? Ou en togolais, ou je ne sais pas. Je ne sais pas parler d'autres langues assez bien. C'est bon ou pas? Donc, si le petit p est inférieur à 0,05, ça veut dire que le bêta est significativement différent de 0 et donc la variable, par exemple, sexe, est significativement associée à la pression artérielle systolique. Et sinon, non. Voilà. So the next question is, when you are looking for, when you're trying to give a prediction of a variable, how do you select? So if you're actually trying to predict a variable, you need to write an equation which will be a good, will give you a good estimation of the one. And so you need to select the right variables. So the question is, how do you select the best models? So how do you select the best axis to predict the y? So before you do a model, you need to examine the literature and the data to determine which are the variables, which are risk factors, and which could be potential confusion factors. So maybe, for instance, you're interested in exercise to predict glucose, but you know that you have to take into account age and various other things to have a good model to predict glucose levels. So you need the risk factors or the things which you're interested in, but also confusion factors. And then you need to aim, the parsimony principle is the fact that you need to aim for a model with the smallest possible number of variables in order to increase the precision of the estimates of your model parameters and facilitate interpretation of results. And so then you check the individual significance of each variable with the response variable. You do a simple linear regression first. Then you keep the variables which are significant at the 20% significance level. And then there are different ways to proceed for each step. So I'm going to explain that again. So when you're trying to construct a model, you're actually trying to give a good prediction. So you have one y, and this is what you want to predict. You want to be able to give the values of y based on a whole load of variables here. So sometimes you might have 10 or 15 variables which you think might impact the one, okay? And so the question is, what is going to be the best equation, beta I xi? What are going to be the best predictors of your y, yeah? So how do you select out of all these? So you have to first examine the literature and decide which variables you think will be interesting. So maybe you're only interested in those two, but you know that these are also impact-wise, so you have to take them into account. And then there are others where maybe you're not sure, but you have them in your model. Then when you have a model, you want it to be good enough that it predicts the y. So maybe you want to put lots and lots of variables in, but if you put too many variables in, you won't give precise enough estimation. So parcimonie, le principe de parcimonie, c'est qu'on veut quand même pas qu'il y ait non plus trop de variables, d'accord? On veut qu'il y en ait suffisamment pour bien décrire le y, mais pas trop non plus, parce que sinon la précision de nos estimations va baisser. Donc c'est un équilibre. And so, d'abord, on fait, la première étape, c'est qu'on fait plein de régressions linéaires simples. C'est-à-dire, on fait y égale bêta 0 plus bêta 1 x1, puis on fait y égale bêta 0 plus bêta 2 x2 séparément, d'accord? Comme ce qu'on a fait au premier cours, séparément pour toutes les variables, ok? Like this. Et là, on regarde la significativité, mais au lieu de regarder 5%, on regarde 20%. C'est-à-dire, on fait une espèce de sélection à la louche. D'accord? Donc on dit c'est significatif si c'est super, au lieu de dire supérieur, si c'est inférieur à 0,05, on dit c'est significatif si c'est inférieur à 0,2. C'est pour être un peu large, parce que parfois il peut y avoir des interactions entre les variables et on ne veut pas tout de suite éliminer des choses. D'accord? Et ensuite, la deuxième étape, ça va être, donc dedans, je l'ai fait pour toutes. Et du coup, sur les, je sais pas combien j'en ai mis, les 8, peut-être que de cette étape-là, il ressort la 2, la 4, la 5 et la 6. D'accord? Par exemple. Qui sont significatives à 20%. Oui? Donc, ici, à la deuxième étape, j'ai X2, X4, X5 et X6. Et les autres, elles n'étaient pas significatives. Le bêta, il était pas significativement différent de 0. Pardon, c'est pas vrai. Voilà, celui-là et celui-là. D'accord? Et donc, ensuite, comment on fait? How do we proceed? Either you can do forward selection or backward selection. So either you introduce one variable in the model, leave it in if it is significant, and then introduce a second variable in the model and a third variable, etc. That's the forward selection, one by one. Or you can say, first we're going to put all the variables in the model. But we start with all of them, and then we take away the least significant, and then the second least significant, etc. Je redis en français. À la première étape, en les regardant une par une, j'ai sélectionné, admettons, 4 variables. OK? Maintenant, je veux savoir comment je peux les mettre tout ensemble. Il faut que je trouve un modèle où il y a peut-être 2, 4, 6, enfin plusieurs X, d'accord? Je veux faire un modèle multivarié. Donc, comment je fais pour passer de mes variables individuelles à les mettre dans le modèle? Forward, c'est quand je dis, OK, je vais commencer. Ma première étape, ce sera de faire un modèle avec Y égale juste le X2, par exemple. Est-ce que le bêta est significatif? Oui, je continue. Je vais rajouter le bêta 4, par exemple. Donc, bêta 2 X2 plus bêta 4 X4. Et je regarde la significativité de ces deux-là. Si les deux sont significatifs, je continue, je rajoute un autre. Ça, c'est forward. Sinon, une autre manière de faire, donc c'est différent, c'est que je commence directement avec toutes les variables. Donc, bêta 2 X2, bêta 4 X4, bêta 5 X5, bêta 6 X6. Et je regarde, je fais les tests pour chacun des bêtas et je regarde s'ils sont significatifs. S'il y en a un qui n'est pas significatif, je le sors parce qu'en fait, à chaque fois que vous refaites le modèle, les valeurs des bêtas et les significativités, elles vont changer. D'accord? Donc, c'est pour ça qu'il y a différentes manières de faire. C'est-à-dire, soit je commence, je les rentre un par un et je regarde ce qui se passe. Soit je commence avec toutes celles que j'avais sélectionnées avec la première étape et je les sors une par une et je regarde ce qui se passe. Et quand je les sors, je sors la moins significative, etc. Vous voyez la différence ou pas? Est-ce que vous voyez la différence? Oui. Donc après, ça c'est déjà des stats un peu plus, de niveau un peu plus élevé. Mais l'idée, c'est que vous compreniez le principe. C'est qu'en vérité, c'est très rare qu'on fasse des modèles avec juste une variable. D'accord? Il y a peu de choses qui sont expliquées qu'avec une variable. On utilise plusieurs variables. Et donc, comment on fait pour les prendre en compte? Donc, on procède par étapes. And so when you look at how do you select how do you compare the different models? Because every time you write an equation, this is a different model, okay? Every time you write y equals da-da-da, x, da-da-da, x, that's one model. So you're writing lots of different models. And how do you compare them? You use something which is called the likelihood ratio test. And this is the null hypothesis of the test is that removing the variable or adding it will not alter the likelihood of the model. So it will not alter the amount of information in the model. So there we reject the null hypothesis if the difference is less or greater than something we want. So we reject the null hypothesis if the p-value is less than 0.005. But okay, for the moment, you can forget the likelihood ratio test. You can remember just about looking at the betas. So that was about multivariable models. So this is kind of next level statistics. But if you've already understood the idea behind the linear regression and having one variable and several variables, that's a good start, I think. So someone asked, what should we do if explanatory variables in the multi-likelihood ratio test show collinearity, especially at the reserve percentages? So in the case where all values from each observation sum up to 1 or 100%. So that's a good point. You cannot have collinearity between variables. You can have some relationship, but if they are collinear, you should only use one, or you should decide on a summary statistic which represents the variables. You can't have, so if the question is whether if the x's have relationships between each other, okay, if they are collinear, so if there's a correlation between the x's, then you can't put them all in the model together. You have to decide which one you use. Right, so we've got 15 minutes left. So I just wanted to give you an introduction on logistic regression, which is a last type of regression. So for the moment, we saw the association between X and Y, that's regression. And we saw always the cases where Y was a continuous variable, then we call that linear regression. But what do we use if Y is a binary variable? We have to use something else called logistic regression, okay? So instead of Y being glucose or BMI or the weight of the baby at birth, those were all continuous variables, the Y's. We can do regression when the Y is a binary variable. So in that case, you have to write the function differently. So this is a model, the logistic regression is a model expressing the association between a qualitative binary variable and one or several quantitative or qualitative variables. So for instance, if Y is a health parameter, disease or no disease, logistic regression estimates the probability of disease occurring when the values of X are known. So actually in the medical and biological field, you do a lot of logistic regression. You're trying to predict whether something is happening or not, the recurrence is happening or not, whether something above a certain threshold is happening or not. So we often use these models. And there, instead of writing Y equals alpha plus beta X, we write Y is equal to 1 over 1 plus exponential minus alpha plus beta X. So why this function? Why is it this complicated function? Because it enables the quantification of the association between a disease and exposure in a way that is coherent with odds ratios. And it also corresponds to the sigmoid shape, which is often observed between a dose and a response. So if you look at this, a linear model is the blue line. So we have X and Y, and the logistic model is the orange curve with the probability of Y being equals to 1 or 0, increasing like this, depending on the values of X. And so when you have a logistic regression, you can see that the form of the sigmoid curve, it can vary, slightly kind of similar to if you have a line. Here, if you look at the red, purple and blue curve, so the first 3 lines here, you can see that the B, the same as our beta, is always equal to 1. And you can see that the slopes here seem always similar, okay? But what changes is the value of A, which is 2, 0, and minus 2. So this A is a bit like where the sigmoid starts going up, and the B is more like the slope of this middle bit of the sigmoid. Whereas if you look at here, curves green, purple, and orange, you can see here that the A is always equal to 0, okay, but the B changes from 1.5 to 1 and then 2 here, okay, so it's like the slope. The B is like the slope of the sigmoid, and the A is like where does it change? So to make things easier, we use the logit function, which is logit P is the Neperian logarithm of P over 1 minus P. And this can be, then you can write it more like a classical regression model with logit of P equals alpha plus sum of beta I xi. And we have the same system as before of how we use the x's. If it's quantitative, you introduce it as it is. If there's more than 2 categories, you have to create the indicator or dummy variables, like we did earlier. And either we have only one explanatory variable or several explanatory variables. And yeah, so then it's the same as what we were saying earlier for the multivariable regression. And the assumptions of logistic regression, there's no condition of linearity, normality, or homoscedasticity, but you have to have independent observations and residuals, and linearity between the independent variables and the beta. There's another, I won't talk about this, this is R squared, is something you can calculate, but we'll look at the example and then we will stop, but the example might help you to understand it a bit better. So we have 400 students, and researchers would like to know what determines the admission to a prestigious American university. So variable Y is admitted or not, so admission or not, and variables X is mark at the highest school degree, average for the last school year, reputation of the school, rated from 1, very good reputation, to 4, bad reputation. So we have 400 observations. The mean mark is 588 and the maximum is 800. The mean is 220. And here there's another mark. The mark at the highest school degree and the average. Oh yeah, the average on the last year. This is the ranking of the school, 1, 2, 3, 4, and this is whether they were admitted or not. So here we have a logistic regression. We're explaining, so do you understand the example? We're explaining, on fait une étude pour savoir quelle est la probabilité d'être admis ou pas à une université. Donc admis ou pas, c'est bien une variable binaire. Donc on prend comme Y, on doit prendre une régression logistique parce que ce qu'on va prédire, c'est la probabilité d'être admis ou pas. Alors que tout à l'heure, quand on prédisait un niveau de glucose ou un BMI, on prenait la variable Y telle qu'elle, et on faisait une régression linéaire. Ici, c'est une régression logistique. Et par contre, ça ressemble à ce qu'on avait avant. It looks similar with the coefficients for each variable. And here, rank, this was a variable with 4 levels. So it was transformed, one variable with 4 levels is transformed into 3 variables with 2 levels, okay, like we did last time. And so here, the interpretation is given, so you can also look at the p-values and decide which variables are significant. So which variables do you think, are there any variables which are not significant in this model? No, they're all less than 0.05. So all these variables are significant. And the way we interpret them is we look at the odds ratio. So we take these values and we take the exponential, on prend l'exponentielle des coefficients pour faire l'interprétation, parce que vous avez vu que la relation entre Y et les X, elle est assez compliquée. Mais quand on prend l'exponentielle, when you take the exponential, then it's a better way of interpreting. So for instance, here, an odds ratio of, say, 2.2 means that for an increase of 1 unit of the general average of marks, so this is the general average of marks, MGL, in the last year of school, the odds ratio of 2.23 means it's the probability of being admitted to the university is multiplied by 2.2, ok? La probabilité d'être admis dans cette université est 2,23 fois plus grande, 2 fois plus grande, si on a une moyenne générale qui est de 1 plus, enfin, la moyenne générale augmente de 1, d'accord? Voilà. Donc, c'est comme ça que ça s'interprète. And then, for the second one, les rangs 2, 3, 4. Donc, 1, c'est une université enfin, un lycée très prestigieux. 2, un peu moins. 3, encore moins. Et 4, donc, c'est des gradations de prestige, enfin, comme en France, des fois, là, ils font les classements des lycées, nanana. Donc, 1, c'est des lycées très bien classés. Et 4, c'est des lycées avec des mauvaises réputations. D'accord? Et donc, là, pour une école qui est classée 2, la probabilité d'être admise est 2 fois moins grande, elle est multipliée par 0,5, c'est-à-dire elle est 2 fois moins grande par rapport au lycée de rang 1. Parce que le rang 1, il n'y est pas sur ça. Pourquoi? Parce que vous vous souvenez qu'on a transformé la variable à 4 niveaux en 3 variables à 2 niveaux. Donc la valeur de référence, c'est la valeur où il y a des zéros partout. Donc ici, c'est le lycée de meilleure réputation. Donc vous voyez qu'ici, plus on descend dans la réputation, donc pire est la réputation, là, carrément, c'est 5 fois moins probable d'accéder à l'université si vous venez d'un lycée d'une mauvaise réputation. D'accord? C'est comme ça que ça s'interprète. On multiplie par l'odds ratio, ça veut dire on multiplie par la valeur donnée, donc 0,2. Donc, quand c'est inférieur à 1, ça veut dire que ça diminue la probabilité d'être admis. Et si c'est supérieur à 1, ça augmente la probabilité d'être admis. D'accord? Donc ça, c'est la régression logistique. Et ça, c'est à nouveau comment sélectionner le modèle. C'est le même principe que ce qu'on a vu tout à l'heure pour la régression linéaire multivariée. C'est exactement le même principe. Donc, what I want you to remember, the difference between linear regression and logistic regression is the nature of the y variable. La différence entre la régression linéaire et la régression logistique, la différence principale, c'est la nature de la variable y. OK? Dans la régression linéaire, la variable y, elle est de nature comment? Oh. Je les vois tous. Électrocardiogramme. Voilà. Continue, quantitative continue. Et dans une régression logistique, la variable y, c'est une variable binaire. Très bien. Non, mais vous vous concentrez, mais je sais que c'est beaucoup de choses difficiles. Voilà, d'accord? Donc, régression linéaire, les deux, ça fonctionne un peu pareil sur plein de niveaux. Par contre, il y a toujours un y et un ou plusieurs x, un y et un ou plusieurs x. Dans la régression linéaire, le y, il est quantitatif. Dans la régression logistique, le y, il est binaire. Et ce qu'on prédit, c'est la probabilité que y soit égal à 1. Et après, la formule à écrire, elle est un peu plus compliquée dans la régression logistique, mais en interprétation, c'est un peu semblable, sauf qu'on est sur des odds ratios et on multiplie, c'est la probabilité qui est multipliée par un coefficient, plutôt que juste l'augmentation de 1 donne pour la régression linéaire. Donc là, on a fini toute cette partie sur la régression. Et la prochaine fois, on fera ANOVA. Voilà. Bon après-midi.